hope you remember when we discussed the reasons for computational fluid dynamics. I'm not going to go over them again. I explained to you that there are several situations where if you recall, the Navier-Stokes equations have very, very few analytical solutions. And for very particular situations of geometry where there's some symmetry and so on. And the only way to solve something for a general geometry, for a general situation, is through computational fluid dynamics. And then there are other applications that you might have not thought about, like in entertainment. There's computational fluid dynamics or physics-based simulation being used in entertainment all the time. Many, all this modern CGI effects have physics-based simulations now that they're not just, otherwise, funnily enough, the human eye is very, very observant, and you can detect when something is not real. It doesn't look real. So they have to incorporate physics to actually make those effects look realistic. And also in games, there's a lot of now physics-based simulation. So that's perhaps an application that you hadn't thought about. And then the final application I showed you was the canine nose, when it was used for simulating the passage of air through all of the labyrinthine connections of the nose, and they were able to find a specific area where most of or a particular sensory area that was very important there was discovered through the simulation. So those are some of the reasons. So let's discuss what are the basic ingredients and what. By the way, what we're going to do is I'm going to make this introduction, and in the next class is going to be in the ECL lab, and it's going to be a practical demonstration of some of the things we're going to cover now, and that's going to be your next homework, okay? Just so you know. So please go to that session on Monday. It's going to be run by Dr. Yokota again, who's going to demonstrate, and I'll have Simon as well, or Anush, probably Anush, help around and walk around the class to make sure that you are able to do it, okay, on that lab. Okay, so there are some basic ingredients for computational fluid dynamics. First, we have to start with a mathematical model. So that is what is it in fluids? It's a set of partial differential equations, PDEs, and or it could be in integral equations in some other applications with the appropriate boundary conditions and initial conditions. I hope you understand all my acronyms there. And the model has to be appropriate, of course, to a particular application. So the application could be, of course, we know there's viscous flow, or it could be incompressible. We could say, okay, viscous, is it viscous? Or maybe we have a situation where viscous effects are negligible, and you might choose to use the Euler equation instead of the Navier-Stokes equation because viscosity is not important. It could be possible. Yes? Initial conditions. Boundary conditions and initial conditions. It's a little s. It's supposed to be smaller, like a plural s. Viscous, or perhaps incompressible. Viscous versus inviscid. Incompressible versus compressible. Some applications will require you to use compressibility. For example, if there are shocks, if the velocity of flow is close to the Mach number, close to the speed of sound, so the Mach number is close to 1, then you have to take into account compressibility effects and the equations that the mathematical model is going to be different. Maybe you can make a 2D or assumption in some situations, so 2D versus 3D. You're going to use different equations or a different model. But in any case, there's always going to be some simplifications already being made here in the choice of the mathematical model. There are always simplifications. Forgive my bad handwriting there. Simplifications being made already. And then we have to, once we have that in CFD, once we've chosen the mathematical model, then we choose what's called the discretization method. The discretization is, after we've selected the mathematical model, we have to choose a way of approximating each differential operator that appears in the equation by an algebraic operator. So this is basically what this is about. So many times, what we have in general, I said, was differential, PDEs, partial differential equations. So suppose that this curly L represents some sort of linear partial differential operator, and it's applied to U, where U is a function like the velocity. And we could have an equation is L of U equal to F. For example, L of one possibility could be that L of U, for example, could be the Laplacian of U, or L of U could be, say, this convective term V dot grad being applied to U. Any of these choices, it just represents a general differential operator, any one that we may have in our mathematical model, and that is equal to something, some other function, okay? That's sort of the general. What we want is from this expression that involves partial differential equations to go into an algebraic AX equals B, where this is a set of linear algebraic equations that we can solve. So this A is a matrix, X is a vector of unknowns, and B is another vector. The right-hand side, these are just numbers. So this is what we want to do. Convert the partial differential system into an algebraic system of equations. This is what's called discretization. And there are many important methods by which one can do this. The one that we're going to discuss is the one called finite difference. We're going to discuss right away. But there are many other possible methods. Other ones are called, for example, finite volume. Conceptually, similar to our control volume approach that we studied before, only the control volume is taken to be infinitely small, and we apply the equations of conservation there. But there are many others, like finite element. And there are other things called spectral methods. And even others. But we are going to discuss only finite difference in this introductory lecture. And that's what you're going to experiment with in your practical, in your next homework, your practical assignment. But note that, again, here in this step, there's, again, an approximation being made. So one always is concerned in computational fluid dynamics about what is the simplification that is contained in the model, the physical model, the partial differential equation that we've used, whether we've taken the flow to being viscid, for example, and so on, and the approximations being made in the next step, the discretization of that model. That is some of the things we concern ourselves with. Those are two steps. Then are another couple of steps involved in the whole computational fluid dynamics, the CFD cycle. So once we have a discretization, many times we want to analyze this discretization. For example, we may want to, in the previous step, the discretization, all of the terms that involve, say, partial differential equations and so on were transformed into arithmetic operations. That is the discretization step that we were talking about. Now, then we want to analyze in the sense of, for example, we want this discretization step, the previous step, to satisfy certain conditions for it to be acceptable. The conditions are, we call them consistency, must be consistent, stability, and convergence. These are things that we must concern ourselves with. For example, stability. Stability has to do with the fact that if you were to introduce a small error in the discretization or in your numbers or in your initial condition or anything like that, you would like the numerical method to be able to continue being close to the solution as it progresses rather than diverge away from the solution. That has to do with stability. Convergence has to do with the idea that if my discretization is made finer and finer and finer, the error has to be smaller and smaller and smaller. Otherwise, it doesn't converge, we say. And so basically it has to do with the level of accuracy. We want to be able to understand when we're doing this, what is the level of accuracy of the discretization. And so this is the analysis stage that is a crucial ingredient in CFT. Then finally we have to solve. Basically we have to obtain we have finally some algebraic system of equations that represents the partial differential equations of the system, and we want to solve this to obtain numeric values of the field variables, velocity, pressure, and so on, on a set of chosen points on the domain, the grid points usually called, or nodes. And there are two options that one can have in this solution phase. One possibility is that if we have a steady problem, then all we need to do is solve an algebraic system. Solve AX equals B, right? But if we have an unsteady problem, a time-dependent problem, then we usually will have to solve in addition some ordinary differential equations, ODEs, ordinary differential equations, by some method that we usually call time stepping an ordinary differential equation in time. And so we need two things for these. We need what we call linear solvers. If you recall from your linear algebra course, do you recall something called Gaussian elimination? Yes. Did you look at any iterative methods? For example, Point-Jacobi, Gauss-Seidel? Does it sound familiar? Okay. There are many other methods that one can use because Gauss elimination is very cumbersome. It takes a long time, and if you have a huge system, I mean, you could have a matrix A that is 1,000,000 by 1,000,000. Okay, it's a huge matrix, and how do you solve that? Gaussian elimination would be hugely slow. So there are other methods, iterative methods, half a dozen other methods that one can use, which are called linear solvers. And there's a wealth. For example, MATLAB has many of these built in that you can try. Then there is. There are many other libraries that have these methods already, and you can use these libraries to try different methods for a particular problem. And for these, we have time integrators, numerical again. And for example, MATLAB has them built in. You have the ODE set of tools there that you can use, and you don't even have to program them by scratch anymore. But one needs to understand them, of course. So that's the basic 4 ingredients of computational fluid dynamics. In addition to that, one also in the end, after one has a solution, would want to visualize. And then because once you have a set of numbers that represent the field value, velocity or other quantities in the flow, you want to be able to use some graphical means to show you that answer in a way that the human can interpret those results and say, okay, the velocity is larger here, there's some recirculation there, this is the point of highest pressure, and so on. You want to be able to visualize, and that's the final ingredient, the final step, many times. Many times you can just deal with a number and be happy, that's what you're looking for, but often you want to visualize, and that is what gives insight to the solution and to the problem. So let me, we had a long discussion about the exam at the beginning of the course, and so let's go on for 5 more minutes, and then I'll give you a short break. Or you want to take a short break now, 5 minutes. Some of you, I know, get hungry by this time, so do you want 5 minutes break now, and then we'll start let's do that. Okay.